Today's topic is the second law of thermodynamics. This is one of those topics that sounds scary at first, but becomes very logical once you see how nature actually behaves. To understand the second law clearly, imagine a small company. There is a boss at the top and several employees working under him. The boss has money, and the employees need money. So naturally, salary flows from the boss to the employees, and not the other way round. Now, if someone claims that money can automatically flow from employees to the boss, we instantly reject that idea because it violates how real systems work. This simple picture already captures the heart of the second law, that natural processes have a preferred direction. Now keep this story in mind and connect it to heat in thermodynamics. Heat behaves exactly like money in this story. It always flows naturally from a body at higher temperature to a body at lower temperature. If you pour hot coffee into a cooler cup, heat flows from the coffee to the cup. The cup becomes warmer and the coffee cools down. We never see the reverse happening on its own, where the cup becomes colder and the coffee becomes hotter without any external help. This directly explains the Clausius statement, which says that heat cannot flow by itself from a colder body to a hotter body. The same idea appears in many other forms. Think about a balloon filled with compressed gas. When you make a small hole in it, the gas rushes out into the surrounding air. It never happens that the outside air suddenly squeezes itself into the balloon. So, the air naturally moves from the high-pressure region to the low-pressure region. Similarly, imagine a tank completely full of water connected to an empty tank by a valve. When you open the valve, water flows from the full tank to the empty one, and not the other way round. Everywhere, nature follows the rule that high goes to low, unless we force it to go otherwise. Now let us move to the second major idea of the second law, which is that perfection is impossible in the real world. Even when things move in the correct direction, they are never 100% efficient. Imagine the government releases $100 under a public welfare scheme meant for a citizen. As this money passes through offices, paperwork, and middlemen, some of it is lost due to inefficiency or corruption. By the time it reaches the person, only $90 or $95 remain. $5 or $10 is lost. In the same way, when energy flows in real systems, a part of it is always lost in an unusable form and never reaches the destination completely. This brings us to the Kelvin-Planck statement, which says that no system can take heat from a single source and convert all of it into useful work in a cycle. A very clear engineering example is a car engine. You put fuel into the engine and expect all of it to turn the wheels, but that never happens. A part of the energy always goes away as hot exhaust gases, noise, and friction. If perfect conversion were possible, there would be no hot gases coming out of the car's muffler, but we clearly see them. Another simple example is a bouncing ball. When you throw a ball upward, it comes back down and bounces, but every time it bounces, it reaches a lower height than before. Some energy is lost to the ground as sound, heat, and deformation. The ball never keeps bouncing to the same height forever. Even our own bodies follow this rule. Food is our energy source, but we cannot convert all of it into useful work. Some energy is lost through sweat, urine, and solid waste. So whether it is machines, balls, or humans, losses are unavoidable. This unavoidable loss is a direct consequence of the second law. Finally, let us connect everything we have discussed to an important idea in thermodynamics called entropy. To understand entropy, think of energy like money that is most useful when it is collected in one place. If you have $100 as a single note in your pocket, you can easily use it to buy something meaningful. But now imagine the same $100 broken into tiny coins and scattered across different rooms, under furniture or sofa. The money still exists, but it is no longer practical to use. You would spend more effort collecting it than the benefit you get from it. Entropy describes this exact situation for energy. When energy is concentrated and organized, it can do useful work. But as any real processes happen in this universe, energy always spreads out into the surroundings as tiny amounts of heat, sound, and vibration. Once energy is spread like scattered coins, it becomes extremely difficult and practically impossible to gather it back and use it fully. This spreading of energy is what we call an increase in entropy. Now, building on this idea, the second law tells us something very important. It says that in any real process, once energy has been scattered like those coins, it cannot come back together on its own. No natural process will neatly collect those scattered coins and put them back into your pocket without extra effort from outside. In simple words, disorder or spreading of energy can happen naturally. But the reverse, which is the energy becoming organized and concentrated again, does not happen by itself. By the way, this idea naturally leads us to the concept of efficiency. Since energy always spreads out and some of it is lost, no machine can ever be 100% efficient. In the next video, we will see how this idea helps us define and understand the idea